All right, so this talk is going to be a little different than usual. No matter what, if I'm standing up here, I'm going to be telling you something about gravity or black holes. That's not going to change. But I don't know if you know, but this year, 2025, is actually the 100-year birthday of quantum mechanics. So, yes, happy birthday, quantum mechanics. Happy birthday. Thank you. So even though, okay, so in 1900 was the first time quantum came to mind with Max Planck, and Bohr's model of the atom came in 1913. But then in 1925, that's the first year that Heisenberg wrote down a complete coherent theory with method of how to calculate things. So that's why we call it the birthday. So I'm going to be teaching you about quantum aspects of black holes. Okay, so first, what's quantum? So the idea is that if you study systems at really short distances, like about the size of an atom, some very bizarre things start to occur. Okay, many things. I just labeled 4 of them. So one thing that happens is quantization. Things that are normally continuous, like energy and momentum, some things become discrete. Like atoms, they can only emit discrete amounts of energy. They don't get to emit whatever radiation they want. So that's quantization. The second thing is quantum superposition. So this is the Schrodinger's cat story. If you all have heard of Schrodinger's cat before, maybe? Well, I know we've got some kids in here, so I'll tell a little bit of a different version. So it's you heard it. What? So the idea is that suppose you've got a cat and you put it in a box where you can't see the cat, and there's like a sleeping potion inside. It can get knocked over, right? If it were a classical cat, it would either be asleep or awake. But if it's a quantum cat, it's both at the same time. And it only chooses one or the other when you open the box and observe it. So this is a very weird thing to have happen. The third is the one that's going to be the most important to us, perhaps, which is the notion of quantum entanglement. So that quantum entanglement is where if you put 2 particles next to each other and they can send signals, what have you. And then you put those in boxes and you take them very far away to other ends of the universe. Then if the person on the right opens the box to observe it, even if the person on the left doesn't open their box, immediately that particle, the state of that particle is selected because it's entangled with the right one. So this is the one that was especially troubling to Einstein. He called this spooky interaction at a distance. We don't like these sorts of things to occur because usually the speed of light moves very fast, but it's finite, right? There's only a finite speed that the information could travel. And this seems like information travels instantaneously. So this is a very weird thing. And then finally, we have something called the uncertainty principle, which is also pretty weird. It means in classical mechanics, especially physicists, what do we like to do? We like to know where something is, how fast it's going all the time, right? It's football season, I believe, if you're wanting to get the trajectory of that football, you want to know when, you want to know where, you want to know how fast. So football fans would be very put out if quantum effects apply, because you can't know both at the same time. You can't know where it is and how fast it's going at the same time. You have to pick. That's very unusual. So this is what I mean by quantum. So what is a black hole? I wanted to go into every item on this list this time about what a black hole is. It's essentially a region of space that's so dense that not even light can escape its gravitational pull. Fastest thing that there is. That's what a black hole is. But for the purposes of this talk in particular, there's really only one thing that we need to observe at this moment. They're really big. Okay, but the one at the center of our, oh, I wrote it down. Oh, darn. The one at the center.
Sagittarius A star.
It is named Sagittarius A star, indeed. Do you know how many suns it is? How much it is?
I think 150,000 solar masses.
You know what, guys? I actually don't remember myself. Yes, yeah.
I thought it was 4 million solar masses.
That could be. How about you?
It was 13 suns.
It's definitely not that. Yeah, it's more than 13.
Actually, that's 4 million solar masses.
You think so?
Yeah,
Look it up. Look it up.
actually it.
Well, look it up. Look it up. But I don't know right now. Rahul, look this up. Okay. But so now it's very big. So what is in the context of this talk, what does this mean? Quantum, right? That takes place on very small scales. So this is actually the least quantum thing that I could even think of, right? It's very big. So what's going on? But nevertheless, you might be tempted to think about regions where quantum things might start to sneak in here, okay? Quantum effects. Two very special places on this black hole are in the very center where there's a singularity. That's a very dramatic place. It's where the tidal forces are so strong that anything that gets so close to it gets pulled apart. So you might think that quantum effects might take place at such a location. Yes.
What's a tidal force?
So the word tides, like we have. So in classical mechanics, some of us learned, including you. Sorry, this is my student. I can pick on him. So, tidal forces mean that if I'm feeling a gravitational force and my feet are closer to the source than my head, like the feet get pulled more strongly, so I kind of get stretched out, and that's also what causes the tides.
Isn't it called spaghettification?
What's that?
Isn't it called spaghettification?
Yes, that's right. Yes, the stretching out. Indeed. Yes. Very good. So that's a dramatic place, and actually the horizon is a bit less dramatic, but you might find in a second. You might find that there are some very special things that happen at the horizon as well, and that's what we'll discover in a few more slides. All right, so it's a timely moment to study quantum applications of black holes, quantum aspects. Not just because it is October 3rd, happily. I didn't choose the date because of this, but also because we have now as a society, we've built a lot of tools, like they can measure gravitational waves, right? We have LIGO, we have Virgo, and we can now measure gravitational waves pretty well. And we might in the future actually be able to maybe measure some leading order of quantum gravitational effects. So it's a timely moment to start thinking about maybe can we detect quantum gravity in some way? Okay, so the way that quantum mechanics sneaks into gravity is actually a very natural way from a physics standpoint. So in physics, there's one connection between the quantum world and the classical world. And the idea that connects it is called entropy. It's a measure of disorder in a particular system, right? So entropy, it has a classical description. So amount of disorder. So here's water, So when water freezes, it gets it gets rigid. And there's not a lot of, it doesn't have a lot of freedom to move. But as you heat up the water, it turns into liquid and gas, it gets more and more disordered. And probably the most robust law of physics across any discipline is the second law of thermodynamics. It says that if the system's left to its own devices, the amount of disorder always increases, which I'm sure that you can imagine, you know, if you don't dust or anything for some time. The amount of disorder always increases. This is the most fundamental law of physics. Most laws get broken eventually. This one does not. Okay, so it's a very important law. So this is the classical, description of entropy. But it also has like a quantum notion to it as well. Okay, and the quantum notion comes from this man named Ludwig Boltzmann, who was alive during this time. And he came up with disorder in terms of the number of microstates, the number of quantum microstates that are available to a system. And you might not be able to tell, but this equation is actually on his grave in Vienna. So if you're in Vienna, you can stop by and say hello to Ludwig. You could use the company. Seriously, he met, yeah. You should look him up, but only when you're in a good mood. Yeah. So what are these microstates? Okay, microstates, they have it's essentially the number of ways that you can assemble your system, right? So suppose if I had a toy box with all these wonderful toys in it, I get to choose different ways that I can assemble these toys, right? And each configuration would be a microstate, okay? So this is the number, the number that we're going to be interested in going forward. We're very interested in calculating number of microstates, especially things like black holes that, you know, you wouldn't think would have any. So we're very interested in the quantum notion of entropy. So this equation, Ludwig came up with this equation in the 1870s. About 100 years after that, two men, so Jacob Bekenstein and Stephen Hawking, they discovered that black holes have entropy as well. Okay, and which is a little bit weird because black holes are classical objects, and this formula for what the entropy of a black hole is one of the most incredible formulas and exciting in the history of physics. Why is it exciting? Because of this. Usually physics is like a patchwork quilt. You know, we've got quantum mechanics over here, we've got classical mechanics over here, special relativity, general relativity, and many times these things don't talk to each other. They're just different. However, in one formula, look at what we have here. We have c, the speed of light. Okay, that's special relativity, that's electromagnetism. We've got Boltzmann's constant, that's thermodynamics. We've got the area of the event horizon, so there's geometry there. This is simply the number 4. This one is h bar. This one is the quantum one. This is Planck's constant. It has quantum mechanics, and this one is Newton's constant that arises in classical mechanics. So the entire undergraduate physics curriculum is here. You know, and that's exciting. And so we look forward to we're going to come right back to this formula. But I'll just say now one more thing that's related to this, just in historical order rather than order of excitement. So their discovery that black holes had entropy meant that it elevated them into thermal objects. Thermal means if they have an entropy, they've got to have a temperature. Okay? Even though, why should it? It's a black hole. Things with temperature radiate, right? But I just told you that light can't escape, right? How can it radiate? This is a crazy idea, really. Until you calculate it, right? So this was the contribution, this is a famous contribution of Stephen Hawking. So Hawking found that black holes actually do radiate, and they have a temperature that's given in terms of these very same variables that we saw before, except here we have written n, which is the mass of the black hole. So you can see that, like, if you have a very massive black hole, like the one in the center of our galaxy, it's really cold, you know. It's not like it's not like it shines very much. This is a picture of not N87. Yeah, this is a picture of a black hole in a different galaxy. So you might think that this is radiation, but it's not. Well, it's not Hawking radiation. So this is the black hole, and actually this is the normal matter that's falling into the black hole. The black hole is, yes, I'll get to you right now. Five seconds. Oh yeah, tell me now. Tell me now.
Accretion disk.
Yes.
It's
kind
made
of
out of matter of the stars and planets that it ate up by the it swells up and it's going in and it goes very fast, like almost the speed of light into the black hole by spinning very fast. And actually, it takes pretty a long time to go in, but that's what the accretion disk is. It's like when it heats a lot of stars. Basically, that's the hydrogen and helium of the star going into the black hole.
Very good. This is indeed like related to the accretion disk, and as this matter is being eaten up, as you so eloquently put it, it radiates and glows, and so this is what this is. So this is not the Hawking radiation, but here's a like a picture of what this is a cartoon of what Hawking radiation is. The way you really calculate it is you have to do a calculation of well, it's called semi-classical. Right? We don't know how to do full quantum gravity, but what Hawking did was he imagined a classical black hole and he put quantum matter around it. Right? And we know how quantum matter works. And it turns out that in this cartoon, if you have a black hole and you imagine the horizon, particle and antiparticle pairs can get created and destroyed all the time. Apparently, our universe in vacuum is actually more like a bowl of bubbling soup. At high enough energies, particles and antiparticles are being created and destroyed all the time. Soup. But if it happens right here at the event horizon, you can imagine one particle getting trapped just inside and one particle being created just outside and it escapes. And this is the cartoon of what Hawking is. Later. But so far we've got our first, this is the first quantum aspect of black holes. So our first quantum aspect is that they have a temperature, and that temperature is created by this semi-classical quantum process of Hawking radiation. If this were the end of the story, it would be all right, but a bit dull, you know? The journey that I'm about to take you on is rather extraordinary. The way quantum mechanics actually comes into the system, you won't be able to predict it, okay? And so, yeah, so this is, by the way, the study of black body radiation led to quantum mechanics. This is the thing I said happened in 1900 with Planck and the so-called ultraviolet catastrophe, if you want to look that up later. And so it might be that studying black hole radiation could teach us about quantum gravity, perhaps. No. But let's get back to our toy box. Now I'll take some guesses from the audience. Which aspect of this equation, which letter or number do you think is the most important? Guesses. Yes.
Is it A?
A, what else? Yes. 4. Yes.
I think it's C3.
C3, yes. Yeah.
Oh.
Or what do you? Oh, it's C3.
I also think it's
Okay, they're all very important. Indeed, the 4, if we could really measure it, that would indeed be the most important, right? We can't measure. So if the 4 is not the one. It turns out that the thing that is the most interesting is, yes, as Donovan put it, it's the A. here, the area. Why is that? Because I just told you about entropy, that it usually goes like the volume, right? It usually goes with the amount of toys in the toy box. But this is almost like the inside doesn't matter. All of the information that I need to describe this black hole is at the horizon, almost as if one dimension were illusory. And in our universe, we actually know of one object that works this way. And that's a hologram. Okay? A hologram is a three-dimensional image here and here that's projected and stored on a two-dimensional surface. So even though holograms appear to be 3D, one dimension you don't really need to have a full description. So the fact that entropy goes like area, this was the catalyst. This is the sort of Helen of Troy of all physics. This, it turns out, is where the quantum mechanics sneaks in. And it takes us in all different directions, which I'm about to explain. And the fact, some folks believe that the reason the entropy is going with the area is because it's dealing with, it has to do with the entanglement between the particle and antiparticle pair, the one that fell in and the one that escaped. So entanglement is going to be a very important idea for us. So now we get in, now we are really going down the rabbit hole. Yes.
I'm sorry, so when you're saying area, is it like the outside area of a sphere?
Yes, that's right. So 4 pi are, square root.
So, when you were talking about the, Hawking radiation,
Yes.
Hawking radiation isn't basically like what black holes see, like almost see how long the universe is gonna exist to like take out one particle by one particle at a time. It's basically like dying by time.
But very slowly.
Yeah, it goes very slow. It could like stay until the end of the universe.
That's some could, right? Because you're with the thing with Hawking radiation is black holes, they are very hungry, right? So they're eating all the matter around them. And they're also radiating. So it's a sort of mix between consuming and radiating. So yes, black holes can be around for a really long time. All right. The most interesting thing perhaps to come out of theoretical physics, not perhaps, the most important thing is the fact that this notion of holography is more general than just a black hole. There are secretly many holographic scenarios that occur. So there are scenarios that I can tell you about in which a classical, not quantum, theory of gravity in 3 dimensions is equivalent to quantum matter in 2 dimensions, in 1 dimension less. And that really is an equal sign. They really behave in the same way. And this is called, I'm only saying to you what it's called in case you're interested and you want to look it up later. The name of this, just a second. The name of this is called the ADS-CFT correspondence. And the original idea was by an Argentinian physicist named Juan Maldacena in 1999. And the paper that proposes this, in that paper, it wasn't 3 dimensions and 2 dimensions. This works for like 5 dimensions and 4 dimensions and 11 dimensions and 10 dimensions. Just as long as they're separated by at least by 1 dimension, it works. So, but the original paper is the most cited paper in theoretical physics history. It has more citations than anything Hawking did, anything anyone has done. And it's likely to remain that way for quite some time. And there's this really fun website that I wanted to point out, this YouTube channel. That if you look this up, you can see like the time lapse from 1974 to 2019 of the most important papers. For a long time, it was the standard model. And then you can see it around the year 2000, things started to change dramatically. So it's kind of a cool website. Yes.
So my question was, what is the closest thing that we have to a quantum object today?
All right. All right. All right. So, I mean, so how about this? We have, like the interior of atoms, right? Electrons are quantum objects. We work with quantum objects. Not me, okay? My colleagues are always studying quantum objects. Like there's superconductors that I'm gonna talk about that are high temperature. These involve quantum principles.
What I mean is like. Atoms are quantum objects.
Yes.
So, what's things are made up by atoms? What?
Well, look, yeah, everything's made up of atoms, right?
Yeah.
So what? Yeah,
So
it's
what is like a full-fledged object?
yeah.
That's just completely.
Let's see. Let's see. Transistor. Let's see. Building one, that's good. There's something here. The building one computers that have fully quantum objects. Let me think. That's good. That's a great question. Thank you for coming up with that. Yeah. Other questions? Yes.
I think what he might have been like also wondering about was like what's the transition between like the size, like how big can an atom get before it becomes like not quantum, say.
Yeah, I do know what you mean. So, to answer that question, so one of the things about quantum mechanics that I didn't talk about, one of the weird things, is particle wave duality, right? So, everything, even me, everything is a particle and a wave both, all right? And there's a thing called the Broly, the wavelength of that wave is the Broly wave. And so you need to think about whether the object's de Broglie wavelength is like a similar scale to what you're looking at. Gotcha. Yes, and that's where quantum comes in. You almost got me on that one. That one I do, yeah.
So on the equation you showed before, it looked like temperature was inversely proportional to the mass, but the entropy was directly proportional to the area.
Yeah.
Does that mean that,
The area is
have-
related to the.
well, yeah, does that mean that as they have more temperature, they have less entropy? As their temperature goes up, their entropy would go down?
So the entropy can never go down, or the entropy of the entire system.
The entropy of the black hole itself.
The entropy of the black hole itself can go down because some of it is into radiation.
Well, yeah, we're saying like, one with black hole with more mass would have more surface area. Yes.
A black hole with more mass has more surface area.
That means that it would have more
Yes.
temperature and a
And
lower.
lower entropy. That's right.
That just feels weird.
Yeah, black holes are weird. They have negative specific.
Oh.
Yes.
Interesting.
Yeah, it's a different object than we're used to. Other questions? Okay.
Are you saying two black holes the same size can't have different densities?
So there's something called, even though I'm gonna violate this later in my talk. Black holes, there's something called the no-hair theorem. So black holes, can only be described by outward parameters, mass, charge potentially, and angular momentum. So if two things have the same mass and spin, they're identical. Okay. So anyway, the example of what this is called is the ADS-CFT correspondence. ADS is the gravity part. It simply means anti-de Sitter space, a negatively curved sort of space. So not what we're used to. It's as if it's like a horse's saddle. And if you draw a triangle on that horse's saddle, the angles don't add up to 180 degrees. They add up to less than that. So this is the gravity theory that we're talking about. And conformal field theory, it means it doesn't matter at all what that is. Sorry, Raoul. who works on this. But it doesn't matter at all what it is, it's just a quantum theory of matter. It lives on flat space, you know, what we're used to, where the triangle corners do add up to 180 degrees. So these two very different systems are equivalent. But this is empty gravity. There's no black holes. There's no black holes on here, right? The black holes were before. And I'm now saying that the holography thing is more general. But what if I now went ahead and placed a black hole in this negatively curved space over here on the gravity side? Let's see what we get on the field theory side. And this is true. So my own PhD advisor, Sean Hartnell, and others came up with a theoretical system called a holographic superconductor. Okay, and the big dream was that there are these actual materials that exist in our universe called high temperature superconductors. So this is a high temperature superconductor. The name of this is bismuth, strontium. No, I can't read that. Wait. Hold on for a second. We'll just take a second. Hold on. Now you know everything about me. Here we are. All right. Bismuth, strontium, calcium, copper oxide is the name of this high temperature superconductor. And high temperature superconductors, they really exist. And but they're very mysterious because, you know, we don't know why we can get such a high superconducting transition temperature. We don't know. If we did know, we could build them rather than just discover them. And then if we could build them, then we could we could, you know, transport energy with minimal energy loss. It would be huge, right? So the goal, the whole dream, was to try to use this holographic correspondence to try to take these interesting two-dimensional materials and build a black hole. And not really, you know, on pencil and paper, folks, on pencil and paper.
How are you going to build black hole?
You build a real black hole by taking a lot of material and putting it into a very small space. For example, the Large Hadron Collider smashes things together, could produce a black hole because it's putting little ones. Okay, it's okay, but it's putting a lot of energy in one space that does that, right? But these ones, the ones that we make up are we just write them down on a piece of paper, all right? So they're not dangerous. But you could try to model this superconducting transition using a black hole. And the one that these folks came up with was putting a black hole that has an electric charge. You put it in this negatively curved space, and you also have this additional field around it, which we call hair. I just said to this young man that black holes cannot have hair. They can only be described by mass, angular momentum, and charge. But actually, in this negatively curved space, we're allowed to do this for reasons that aren't important right now. I can describe. So it's okay. And it turns out that. So, what plays the role of temperature here? The role of temperature in the superconductor is played simply by the temperature of this black hole, right? And it turns out that if you start at very, very high temperatures, all this field, it's set to 0. There is no activated field. But then as you cool down the temperature, then this field starts to bubble up. And that actually, that kind of mimics the superconducting transition. So there are still a lot of people trying to work on ways to study these higher temperature superconductors using black holes. And this is a true story. I'm not making this up. I studied this during my PhD as well. Though I don't do it anymore. It's a very hard question.
So like, what is the hell then?
What is what?
So, is the hell, like, what is the hell? So it's stuff outside of the black hole that we're using to understand the black hole, but like.
Right, so this is a particular type of field. We have like electric fields and all that kind of stuff. It's a vector field. This is another type of field that's called a scalar field. We don't really have these very much. It only has magnitude and odd direction. You can think of it a little bit like a temperature field. You're just turning on some sort of quantity around the black. Yeah. Yes.
You mentioned that we already have what they find high temperature superconductor material. Where do they find it? How much of it is in
You mean how much did I get? You don't have. Yeah, this one is for my condensed matter colleagues, unfortunately, but there are people here that work with high temperature superconductors, so I can find out for you. Okay. Other questions, and then this is why this was such a hard topic for me to work on, because not only did you have to know all about gravity and quantum effects, you have to know all about condensed matter as well, which is very hard. No vote. Yes. I see, yeah.
For one of the previous questions about the two black holes are like coming in contact with each other, do they possibly repel each other the same way that if you get two magnets, you put the same polar sides next to each other, that they end up repelling each other?
Sure. I mean, the charge that a black hole has, the ones that we have in our universe don't appear to be charged, but in theory you would go. And if they have two opposite charges, they can repel.
Would it be off of the charge or off the
Off the charge. Because yeah, otherwise gravity is always trapped. So. Other questions? Yes. Yes.
So I thought if a black hole came close to another black hole, a black hole that's bigger would just automatically eat the other.
And that is fast, right? These things, these charged ones are kind of a theorist's toy. We don't see these ones, but we do see in our universe the spinning ones. But you're right, the bigger black hole gets together up, and the result is always grows.
So it's orbit in a way.
We'll actually talk about that later. You'll see exactly. You know exactly what happens. All right. Bet you didn't think black holes were superconductors, and you probably still don't. But that's okay if you will think about it. All right. So. Okay, so coming back, so that's what I'm going to talk about with holography, but we can take this notion of quantum entanglement a little bit further. And I kind of wanted to tell you about a pretty fun notion that other people have worked on. So there's this dubious looking equation here, ER equals EPR. So this has been a pretty important idea, and it ties back in with quantum mechanics, which is why I wanted to bring it up today. So the people who came up with this are that same Argentinian Juan Maldacena and Leonard Susskind, who's from the Bronx. I don't know if I mentioned him, but he's from the Bronx. Yeah, he's a nice guy, and he's a smart guy. So they came up with this ER equals EPR slogan. And what does it mean? These stand for people's names. So E is for Einstein and R is for Rosen. And they wrote a paper in 1935 that was the first paper to introduce the concept of a wormhole. You know, wormhole is something where you can start at one point in space and just immediately get transported to another place. So that was in 1935. Oh, I got a question about that, yes.
So like, I know a wormhole. It's two black holes connected together that can like travel space really fast. And they're not like normal black holes. They travel through.
This is a very good intuition. In fact, they don't have to be two sides of the black holes, but actually, some people think that that's what black holes really are. They're just one side of a wormhole. So it sounds like you know an awful lot about this. And that's true. Yeah.
I like black holes so
Okay. Oh shoot. So these are, I won't talk about my glasses, but these are bifocals and only the bottom part is useful, so I don't like to, maybe I'll take them off when I'm walking up and down. Alright, so, so this is a paper about introducing wormholes in 1935. And over here, the names, the E still stands for Einstein, the R still stands for Rosen, and the P is this other person, Podolsky, joined the group. And this actually also highlights a fun thing in theoretical physics, where if you write a paper, the order of the authors is always alphabetical. So for better or worse, you can never tell like who led the project or who came up with the ideas. So it's always alphabetical. All right, but it's probably Einstein, right? Or maybe not, you know? Maybe that's why he's so famous, because he starts with the letter E. Right, maybe it's in Somologikov, he went to, you know. But now, so their paper was about something completely different, right? It was about quantum entanglement. This is the paper in which Einstein wrote that there's spooky interaction at a distance, and this is very troubling. And in this paper, they called it the EPR paradox, because they thought quantum mechanics couldn't be complete if information didn't travel like if information seemed to travel faster than the speed of light. All right. So even though these papers were written in the very same year, by the very same people, somehow they did not want to put together the fact that perhaps this spooky interaction at a distance is occurring through a wormhole, right? So this is ER equals EPR, means that an Einstein-Rosen bridge is equivalent to quantum entanglement. And this led to this started leading to the idea that perhaps space-time itself is built up of entanglement. So these are the very, I don't know, forefront of ideas right now, that entanglement is potentially the most important thing to study. So. Okay. All right, this is my favorite, and I'll go over it. I know that there are equations on here. Don't panic. All right, they're still quantum, right? So now remember Boltzmann's our Boltzmann's equation here. We are interested in calculating the number of black hole microstates and finding out everything we can about them. What even are they? What does that even mean? We're very interested in these. And it turns out that black hole partition function is another thermodynamic object. It's the most important one, because not only does it tell you how many microstates you have, it tells you how they're arranged as well. So if you know this, you know a lot about the system. And it turns out that certain black holes, partition functions for those, are like a zeta function, like this very famous Riemann zeta function. Has anybody heard of the Riemann zeta function? Few people. It's cool. It's cool because if you answer questions about it, you win $1 million. All right, yes. Then this is true. Last question. You have a question about that? What do they want to know? What do they want to know? I'll tell you what they want to know. I'll tell you what they want to know. So this is the Riemann zeta function. It's a function of S. And they want to know every value of S that you can plug in that makes the right-hand side equal to 0. And here are 3 of them. Here are 3 of them. If you can prove that all of them start with a 1/2, you get $1 million. This is one of the most famous prizes. This is one of the most famous puzzles of all time. It's called the Riemann hypothesis. So you can write to the Clay Mathematics Institute. I'll give you their site. So the main takeaway about this particular zeta function is there are 2 things really. The zeros are very interesting. It's not clear from this, but the zeros seem to tell us information about the distribution of prime numbers. So that's important. They tell you something physically interesting. And the second thing is the Riemann hypothesis, you get $1 million. So what does this have to do with black holes? I'll now change slides and tell you the equivalent of these 2 points for black holes. So this partition function for these special black holes are also zeta functions. And the zeros of it give you physically interesting, like they give you physical data. So they tell what the zeros are happen to be about black hole quasi-normal modes. So here's a picture of illustrating what quasi-normal modes are. This is a picture from LIGO. And LIGO captured 2 inspiraling black holes and a merger and this ring down phase. So you can imagine 2 black holes spiraling, spiraling, spiraling. They're merging together, and then they form 1 black hole. And this ring down part, this is a quasi-normal mode. Quasi just means it decays. That's all. So the zeros of this partition function, they give you these. And since these quasi-normal modes describe perturbations to black holes, as you can see from these pictures that like once the black holes are all almost merged, you kind of have a classic black hole plus a little bump. So these quasi-normal modes are very important for studying like perturbative quantum effects, like the classical limit with just a little bit of a perturbation. So these quasi-normal modes are very important. So we can study them in our own right, or perhaps we can even study this famous Riemann hypothesis, a version of it, using black holes. So now we've just come full circle. You know, we've got superconductors here, we've got the Riemann hypothesis. Black holes can do anything you want, okay? So that's it. If I'm here for forever, if you have questions, go ahead and let me know. I think Sajak has put, we might also be doing stargazing of some sort as well, or a quiz. There's still other stuff going on, but questions? Yes.
So my question is the hole that is bigger than the black hole that's near it, it goes in, will it just gain its size?
Yes. In fact, boy, oh boy, it would gain in size. In fact, you know what? That's how they knew that black holes had entropy. The fact that every time you put another one in, every time the black hole ate another black hole and ate another black hole, it kept gaining in size all the time. And that, somebody said, sounds a lot like the second law of thermodynamics. And that's precisely how it was discovered. Yes. Question.
Could you go back a slide for a moment, sorry?
No, go ahead.
So with the quasi-normal mode.
Sorry, I'm trying to go back. Okay, yeah.
So with the quasi-normal mode and the frequencies, what does it mean by the frequency of the quasi-normal?
Right,
How often it happens, or like way which it moves?
No, so the way you write a wave. So this is like a sinusoidal thing. And it has a particular argument. It has a wavelength that is like tells you how far these things are, and it has a frequency. Yeah, which is essentially related to this wavelength. So you can see the frequency. Yeah, if this were a plot in time, it would be how much time it takes essentially for one part of the wave to come back this again. Yeah.
So, but then if we look at the whole white side, is that just a small decrease in wavelength? And.
Or well, this is a decrease. This is mostly not a decrease in wavelength, actually. This is a decrease in energy. Amplitude, right. That's right. It's the same thing. And also, so this is with a black hole merger, but if you had just any normal, if you had a black hole itself, and you sent a wave inside like light is a wave, right? Or another particle, you would see that its amplitude goes like this, but then it loses energy as it goes in. And this part is called quasi-normal. And out here it's like, here is one. Because it's decaying.
Because the amplitude, we would expect the amplitude to increase because of entropy, but then it decreases.
We don't, left to its own devices, the amplitude would be the same.
Oh, okay.
But it's because of the black hole horizon that it kind of decays a bit cold.
So if two large black holes collide, would that make like a sound effect that would spread throughout space?
Let me see. So that's a bit of a tricky question because there's this famous phrase that in space no one can hear you scream. And the reason is because sound waves require a medium. So not really, because there wouldn't, unless there was medium that was dense enough to carry that sound wave. Yes.
Wouldn't that be like a gravitational wave though?
Yes, there is a gravitational wave, but gravitational waves are what is called transverse. Like the oscillate, it's like this wave. Like the direction of propagation, the amplitude is like this. And the sound wave is different. The sound wave is a compression wave. I think I saw, yes.
So are white holes a real thing or like something like that?
It's an idea. So a white hole is so if you let's see. Yes, it's an idea. Essentially, if you time reverse a black hole, so I can tell if we have time. If you were inclined to know more, I can draw you a Penrose diagram later. But I'm afraid it will get far afield. Yes.
Dwarf are things.
What's that?
Black dwarfs are things.
Okay,
That's like white dwarfs.
yes.
So, we know black holes grow, but they also shrink and just disappear.
They shrink, that's for sure. Do a Hawking radiation. If there's no matter to feed the black hole, it will shrink because of Hawking radiation. Does it disappear? Unknown. Perhaps it leaves a remnant, perhaps not.
But like, what about like in that particle collider, right? You said that there's potentially many tiny black holes that get created. I guess those disappear because nobody has seen them, or would they be too small to even measure?
Yeah, no, this is a good question. I think, I'm not quite sure on that, but like if certainly no one has like reported like the rate at which they decay again. Like this is not. Oh boy, let's see. Look over here.
So when a black hole collides with another one, what happens to the singularity? So they immediately combine and basically.
But you can never tell what happens to the singularity. It might not even be there, right? It's a classical, the singularity happens from the classical theory, so perhaps like, yeah, but you cannot yet know what happens. Let's see, yes.
So, say there's one big black hole, this black hole is bigger than this other one,
All right.
and
Yeah.
it is a quasar.
Well, quasar is not a black hole, but
Well, the bigger one is.
and then there's a big black hole in the quasar. Yes.
The No, smaller black hole is not.
Okay. That would be a really big quasar probably, yeah, let's see, yes.
The beam, it's the smaller black hole. What happens to that black hole?
No, it will just simply absorb the energy. Black hole, it won't like float or anything. It will simply absorb the energy of the beam and go later. As it absorbs that energy. Yes.
So you know when you said that everything could be a 3D hologram? How do you know that we have?
You know what? Like when the first time I gave this talk. I had some pictures of Scientific American magazines. Scientific American is a magazine that people like kind of respect. And like, and they had the image, the front page was like, the universe is a hologram, and then one of them said, you are a hologram. So the people, yeah, they've gone down that route. But one thing to say is, you know, human beings are extremely complicated systems. And even though a black hole is in a way complicated, it's also very simple, right? You don't even know what's going on. Right? So usually like quantum things, in holography, one side is quantum, right? Usually like those sort of things don't apply to people because we're just too macros. But yes, people have gone down that. Yes.
With like not the star black hole, but like the section, or like it's mostly black hole, and then there's a section of the other black hole separate.
Yeah.
Is that going to only be there at the zero, the quasi normal mode?
Yes. Then they become
Then
safe.
they become, so like, do we have a concept of how long that would be the case?
What is the range? Oh yeah, I mean,
We've seen models, how many big it's
it is known by human beings. It's not known by me. But this information is known. Yes. What was your question?
He's talking about.
Yeah.
Or something like going into black hole or something.
Yeah. Hawking radiation.
When one of them goes out, it's smaller. And when it gets too small, it explodes in supernova explosion.
See now here's where we have to disagree. I was with you up until then. I was with you. Okay, I don't wanna, it's 9, so I'll still be here, but I'll release you to. Thanks so much, you guys.